primeira coisa que eu tenho que falar é que não vou poder cumprir a minha promessa de justificar exatamente aquele argumento de trifurcação, mas vou tentar. Então, tipo, se você lembra, o argumento era de dizer que se você pega 3 pontos no bordo da caixa, você pode ligar eles no meio. Sorry. So, the idea was, yeah, okay, so what I was saying last time is that basically if you had a certain number of points touching the exterior of a box, you could choose 3 of them and link them to 0 using 3 paths that don't touch each other. Okay, that was the statement. Okay, so let me try to give you a justification, which is okay, but maybe okay. You tell me what you think about it. So let's first start with d equal 2. Okay, and with d equal 2, basically, the only problem would be if you have a configuration like this. Okay, if you have this, then the first step of this guy should be there. And okay, so things cannot avoid themselves. But as soon as you have something like this, basically, okay, you can do. Okay, and all the other options are kind of less complicated than that. So if you have at least 4 points connected to the box, then you can find 3 of them which are not packed in a corner. Yes? Okay. Because if you have 4, then okay, they cannot be, well, all subset of 3 cannot be like this. Okay, so that settles the case d equal 2. Now if d is larger than 2, basically what you want to say is project into dimension. Okay, so, and this is something you can do because basically because all your points are, okay, so basically your points are disjoint, okay? So if you have x1, x2, x3, basically you can find 2 coordinates, okay, for which the projection of these 3 points will be different. Okay, so basically there exists I such that, okay, x1, I, okay, maybe put this there. Is different of x2i, and there exists j such that x1i is different from x3 from x3j. Okay, so therefore, if I project on, you know, z times something times z times z times something. Okay, so zd, it's just this, where here you have j minus 1. Okay, I minus, okay. I suppose here, without loss of generality, that j is larger than I. Okay, 1 is larger than the other 2. Okay, so here I would have I minus 1. Here I would have j minus I minus 1, and here I would have d minus j minus 1. But I mean that this is zd. I can project it on z2 just by keeping these 2 coordinates, and then these 3 points will be different. Okay? Now the problem, and then to construct my path which go to 0, basically, what I would do is first, well, take a path that takes x1 to its projection, x2 to its, well, x1 to its projection and the other coordinates being 0, and x2 to its projection and the other coordinates being 0. And this path, okay, well, just make, well, you take the coordinates sequentially and you bring them to 0, and they don't touch each other just because the coordinates there remain different. Okay, so then you're back to this point. The only problem is that you have 3 points and you would need 4 to conclude. Okay, so the claim is that if at the beginning you have more than d plus 2 points, then I claim that there exists a projection such that you can find 3 points which are not located like this, which are not in this configuration. Okay, and you need d plus 2 points because, okay, for d plus 1, okay, I'm just doing this thing in dimension 3, but if your points are located like this, you see, in any two-dimensional projection, you will have this. Okay, but this is the worst case, and as soon as you have more than d plus 1 points, then you cannot have this configuration, and this means that okay, you have to do a bit of work, but there is a projection so that you find this configuration. Okay, so I think this is one way to see things. It's important maybe to have an argument to do things in dimension larger than 2 because you can't do drawing. But on the other hand, in dimension larger than 2, also this is not so much of a problem. You have much more space to move around, so yeah, okay. But okay, I promised you that I would try to do something, so this is my attempt. Okay, so okay, now what we have done so far is we have shown that on ZD there is a value PC such that if P is larger than PC, then you have one infinite cluster. If P is smaller than PC, you have all clusters that are finite. Okay, so now what we are going to do during the remainder of this course, well, this part of the course which is about percolation and ZD, is okay to try to prove that PC is equal to 1/2 for Z2. But, okay, I put that as an objective, but actually what we are going to prove on the way, okay, to show this, there are things that are, okay, valid in a much larger setup and that are interesting in themselves. So, okay, and what we are going to do today is basically to show that theta of 1/2 is equal to 0, meaning that PC of Z2 is larger than 1/2. Okay, so basically to prove this, there are two ingredients. One is a smart trick by Zhang, but the other is something which is completely general, which is called Harris inequality, and which tells you about positive correlations of events for product measures. Okay, so now I can try to see. Okay, so let me first introduce a few notions. So, okay, so let me introduce the notion of increasing events and functions. So the first thing we do is we introduce another relation on omega. What we say is that omega is smaller than omega prime if omega e is smaller than omega prime e for all e in E. Okay, so it's just the coordinate-wise order. If you remember the definition of an order relation, it's not difficult to show that this is another relation. Okay, it's transitive and reflexive, and I think this is all you need. Okay, so now we say that an event A is increasing if whenever you have two configurations which are ordered, then if one belongs to A, the other belongs to A as well. Okay, and a function f from omega to R is increasing if whenever two configurations are ordered, the values of f are ordered. Okay, so what's important here to remark is that my order is not a total order, so if you take configuration, it's you don't have. Okay, this thing is not true in general if you have two configurations. Okay, and as soon as you have two edges, okay, you can find counterexamples. Okay, 0, 1 and 1, 0. Okay, they are not comparable. Okay. And the other thing is that saying that an event is increasing, it's the same as saying that its indicator function is increasing. Okay, so function that is equal to A, 1 for configuration that are in A, and 0 for configuration that are. Okay, and yeah, even though this thing, all of this corresponds more to non-increasing than increasing, okay, people always say increasing here. Okay, so what is FKG inequality, or Harris inequality? Well, it says that if f and g are bounded functions, and okay, I'm going to put an extra assumption, but which is not required, but depending only on the state of finitely many edges. Then if f and g are increasing, then the covariance between f of omega and g of omega is positive. So this means that the expectation of the product is larger than the product of the expectation. Okay, and this is under the percolation measure. Okay, so if A and B are increasing, and star is satisfied, then this is the probability that I want to say. Then the probability of the intersection is larger than the product of the probability. Okay, so here, okay, for the sake of the proof, I'm going to make this assumption that the functions or the events that I'm considering are depending on the state of finitely many edges. Actually, this is not required because you can extend the result to general events. But for this, you need martingale theory. So you can look at the references in the lecture notes if you want to know about this. But let me give you basically show you where the problem is when you want to extend this to where it's not trivial to extend, but why it's reasonable to think that this will extend to events that depend on finitely many edges. So okay, so just a small digression. So if A and B are increasing, then what you can do is to say, okay, there exists cylinder events AN and BN such that PP of A delta AN and PP of A delta BN goes to 0. Okay, sorry. Okay, so you know that you can from this, it's not difficult to show that you also have this. Okay, if you remember okay, maybe you have to do it by hand, but this is not that much of a big deal. Okay, so basically, if you want to prove FKG inequality for A and B, maybe you can just apply it for AN and BN. And then you're done because you can pass to the limit. Okay, so does anyone see a problem with this? I cheated somewhere. Okay, so, I mean, why would this be true? I have not assumed anywhere that AN and BN are increasing events. Okay, so in order to make a reasoning like this, you would have to show that you can approximate A and B by increasing events depending on finitely many edges. Okay, this is. Okay, I don't know. Okay, so this is, I don't know if you can show this directly, but you can show the equivalent of this for functions using martingale theory. So therefore, you don't have any trouble, because this is stronger than this. Okay, this is simply this applied to indicator functions. But okay, but this here. Okay, gives you the reason why I will be able to apply this without this assumption, because in all the cases where I'm going to apply this, even though I will not have cylinder events, it will be very clear that I can approximate them by cylinder events that are monotone. Okay, when I apply FKG inequality without this assumption, I will talk back about this. So now let me make a few observations about the results. So first thing is that there is another way to rewrite it. Okay, in the case of events, it's to say that the probability of B knowing A is larger than the probability of of B. And this is kind of natural, okay? A is an increasing event. So the idea is that when you condition to an increasing event, basically you're opening more edges in your environment so that you will make other increasing events more likely. Okay, so. Okay, and then you have a few corollaries. So if F is increasing and G is decreasing, then you have, okay, so maybe I should say that. F is decreasing if minus F is increasing, and A is decreasing if the complement of A is increasing. So these are definitions. Okay, and now you have that if F is increasing and G decreasing, then the expectation of FG is smaller than the expectation of f time the expectation of g. Let me check if this is and f and g are positive, are non-negative. Yes, I think there is no problem. Okay, let me just check. When you apply this to minus f. No, you don't need this assumption. You don't need this assumption. Okay? Just apply fkg to f and minus g and you're done. So the same is true for if you have two events which have opposed monotonicity. And well, the other thing is that you can apply also fkg inequality to more than two functions. So if f1, fk are non-negative and with the same monotonicity, then what you have is that EP of f1 times fk is larger than the product from I equal 1 to k of E fi. Okay, so what I mean here is that if the f's are all increasing or all decreasing, you have this. So for k equals 2 is just fkg inequality if f1 and f2 are increasing. And it's an immediate consequence if they are both decreasing. And if k is larger than 3, basically, it's an exercise. Okay, so prove it by induction. Okay, and in the induction, be careful, look at where you use this assumption, because it's necessary. Okay, and from this in particular, what you have is that, okay, if you have a bunch of increasing event, then they are like collectively positively correlated in this sense. The probability of the intersection is larger than the probability of the product. Okay, simply because indicator functions are non-negative. Okay, so any question about the statement and the consequences? Okay, so the reason why it has two names is that it's actually more general than just an inequality for product measures. So we are going to reprove an FKG inequality in the case of the Ising model. But the case for the product measure is, strictly speaking, is called the Harris inequality, and it's much older. Okay. So, so now I'm going to prove this. And in fact, I'm going to prove something which is slightly more general, which is valid for all product measures on a finite power of R. Okay, so let me. Okay, let's first look at the case where basically you have a couple of increasing functions, and they are real valued. So let f and g from R to R be increasing and bounded, and let, okay, and yeah, so because they are increasing, they are measurable. So I don't have to worry about that. And let mu be a probability measure. So by this, I just mean a measure such that which has total mass 1. Okay, what I claim is that the integral of f g d mu, it is larger than the integral of f d mu times the integral of g d mu. It looks very much like this. Okay, so has anyone any idea of this proof, or anyone already sees saw this? It's kind of a simple statement, right? Okay, so somehow it relies on a kind of trick which I think is probably difficult to find on its own. So the idea is to look at integrating something with respect to the product measure, and this makes sure that this thing is positive. So what we are going to look at is okay, so what I'm claiming is that this is positive. Or this is non-negative. Okay, so does anybody see why? Okay, so just look at the quantities that we are integrating here. Yes?
Can you divide the x by either equal to y, and then the integral, but this doesn't happen, and then since they are increasing, the g of inside the x's that are bigger than y's, both will be positive, the terms.
Yes.
And in the others, they will be both negative, therefore the terms are both positive, therefore the sum will be negative.
Yes.
Positive.
Yeah. So yeah, so you can make this division, or just say, okay, these things, they always have the same sign because they have the same size as x minus y. So therefore, the product is always positive. Yeah, so it's exactly this. So now you just have to show that, well, this is actually the difference between this and that. Okay, but this is not, okay, this is kind of immediate. Here, when you expand, you have 4 terms. Okay, so you have 4 terms in the expansion. Okay, so if I look at the x, x, or y, y terms, the diagonal terms, okay, so I have the integral of fx, gx, mu dx, mu dy. The integration with respect to y gives me 1. And the expectation with respect to x gives me this. So integral of fg d mu. Okay, so I have the factor 2 in front, and xy, yx yield 2 integral of f d mu integral of g d mu. Okay, because in the first case I have the integral of fx gy mu dx mu dy. Okay, you can use Fubini to separate the integrals. And you have a minus in front because each time you take the cross term, you will get a minus term. Okay, so what you have is really twice the difference here is positive. So this means that one is larger than the other. Yes. Yes. Yes, yes, yes. And it's not, I mean, you know that integrable functions are, okay, L2 functions, they can be approximated by bounded functions. So here, if you want, you can put f and g in L2. Well, just to make sure that this is finite, but actually, you can put f and g in L1. And this will still be true, and this can be infinite. Okay, let me check that I'm not saying anything. Let's put them in L2, okay? Because I'm not sure that the arguments gives you that the negative part of this is integrable. To say that this integral is infinite, okay, you need to say, okay, the positive part is the infinite integral and the negative part is the finite integral. I'm not completely sure the argument gives you this, so, but f and g in L2, this is fine. Okay. So once we've seen this, maybe we can prove something which is a bit more general than this. So let me give you the general version of Harris inequality. And well, it's exactly the same, except that I'm going to move to change a bit the definition. So on Rk, I would say that f from Rk to R is, okay, no. I put an order on Rk, so I say that x is smaller than x prime if for all I in 1k xi is smaller than x prime I. Okay, the same order as before, coordinate order. And I say that f from Rk to R is increasing if, well, x smaller than x prime implies f of x smaller than f of x prime. Okay, and now what I'm claiming is that if mu is a probability on R, Okay, what I have is that f, g are increasing and bounded, then the integral of f g mu k du k is larger than the integral of f d mu k. Okay, let's not put any times the integral of g d mu k. Okay, and the idea is that the proposition corresponds to the case mu is equal to 1 minus p Dirac on 0 plus p Dirac on 1. Okay, so is everybody happy with this? I'm not cheating, but it's maybe it's not completely obvious why. If you prove this, and you've proved that. Okay, so one first I can say is that, okay, if your functions depend on the state of finitely many edges, it means that basically, okay, if you call E1 to EK these edges, basically in the end you have functions of, you can reduce this F and this G to, I don't know, F hat, G hat, which are, or F star and G star, which are function from 0, 1 to the k to the r. So they are indeed functions of a product space, of a finite product space to r. Okay, and they are increasing function in this space for the coordinate order. Okay, just by the assumption that the original functions are increasing. Okay. Okay, now, if you have a function on Rk which is increasing, okay, its restriction to this will be increasing. But basically what I'm telling you is that you can use the thing the other way around. So maybe you have to be a bit careful here, but this is just to say if you have a function which is increasing on 0, 1 to zk, you can extend it to Rk. Okay, because here to apply this result, you need a function on Rk. Okay, so I don't know. Okay, so would anyone be able to define me an extension of f? I mean, it's not unique, so there is not only one solution, but an extension of f which is increasing. If I give you a function on this set, which is cardinality 2 to the k, can you extend it to Rk in an increasing manner? Okay, so, well, the idea is simply to well, replace somehow these coordinates by zeros and ones. So, and you want to make sure that you're doing this in a way which is not stupid. And so maybe if you define x bar, which is equal to 0 if x is smaller than 1/2 and 1 if x is larger than 1/2. This works. Okay, and you can check that indeed this works. Okay, but here, I mean, here I could put anything between 0 and 1. This would work the same way. Okay, I just make sure that f bar takes the same values as f, and yeah, if it's larger than an element of where these things are larger than 1, I put the value corresponding to 1. Okay, so therefore now once you have this, okay, basically you say, okay, if I want to prove this, I transform my f into some extension, I apply this to the extension, and okay, and this is a much more general result. And for convenience, I'm presenting it only for mu to the power k, but it's valid for any product measure. Okay, so I could have, instead of mu to the power k, just the product between mu1 and mu2 and until mu k, where all the mu i's are probability measures. So any questions before we start the proof? Okay, so what we are going to do is to prove the result by induction on k. So we've proved it for k equal to 1. Okay. And so we are going to assume that we have proved it until k minus 1, and show that it remains true for k. So for this, I will need to introduce auxiliary functions. So okay. So maybe you forget that f bar, the notation f bar has been used here, but now we can forget about it, and I will use it for something else. So I defined, okay, so I say that x in Rk, okay, I write it as x bar xk, where this is an element of Rk minus 1. Okay, and now I want you to check the following properties. So first thing is that for all xk in R, what I have is that the function that to x bar associate f x bar k, xk, is increasing. Okay, it's just a consequence of the definition. It's immediate to check. Okay, so if you fix one coordinate and you look at this as a function, okay, of Rk minus 1, then it's increasing. Okay, and the same is true. I'll only write things for f, but it's also true for g, of course. The other thing, I will defend f bar of x bar to be, no, f bar, sorry, of xk. So f bar is a function from R to R which to x, but okay, let me write xk, associate the integral of f x bar xk mu k minus 1 dx bar. Okay, or okay, maybe if you prefer f x1 xk minus 1 xk. I'm integrating with respect to everything except the last coordinate. Okay, and what I'm saying is that f bar is increasing. Okay, so, well, maybe, okay, I will just prove this to make sure that I'm not cheating anywhere, but what I have is that if x k is smaller than x prime k, then what I have is that for all x bar in R k minus 1, I have f, I have x bar xk smaller than x bar x prime k, which implies, because f is increasing, that f bar xk is smaller than, fx bar xk is smaller than fx bar x prime k. Okay, and now I can integrate this inequality with respect to the product measure mu to the power k minus 1, integrate with respect to x bar, and I get that f x bar of xk is smaller than f bar of x prime k. Okay, after integrating with respect to the first k minus 1 coordinates. Okay, so once we have this, well, the induction will work almost automatically, provided we start in the right order. So, okay, what are we trying to? Okay, I erased the theorems. That's very good. But we want a lower bound on the integral of f x bar xk g x bar xk mu k minus 1 dx bar mu dxk. Okay. So, well, the first thing I can do is look at what I have inside. Here, I have a double integral, you know. Okay, so this is okay. Maybe I should start it from the start. This is the integral of fg mu k d mu k. Okay, I'm just using Fubini here. Okay, now I can use fkg here for what I have inside, because once fk is fixed, I have two increasing functions, and they are bounded. Okay, so induction, so this is okay. Harris for k minus 1. So using the induction hypothesis, this is larger than the integral, okay, and then I have to write this as a product. So I have integral of fx bar xk mu k minus 1 dx bar. The same thing with g. And mu dxk. Okay, now these things, well, they are simply equal to f bar of xk and g bar of xk. And now we can use Harris inequality in the case, in the one-dimensional case. This one we have, it's not even induction, it's something we have explicitly proved. So using the case k equal 1, we get that this is larger than integral of f bar xk mu dxk g bar xk mu dxk. And now if you replace f bar and g bar by this expression and use Fubini, you just see that this is just equal to the integral of f d mu k integral of g d mu k. So yes, basically here the biggest work you have in the proof is introducing the right notations, looking at the right quantities. And then it's kind of obvious how to do. So, okay, I mean, here I've done first k minus 1 coordinates, then 1. You can do it also in the other direction. Fix k minus 1 coordinates, use fkg for the last one, and then use the induction hypothesis. This works as well. Okay, so now we are going to use this in order to prove that on Z2, for p equal 1/2, you don't have percolation. Okay, and this is theorem on Z2. We have P the probability that 0 is linked to infinity for p equal to 1/2 is equal to 0. This is the same thing as saying that theta 1/2 is equal to 0. As a consequence, PC of Z2 is larger than 1/2. Okay, as a consequence of this, okay, we'll see that when you prove that PC is smaller than 1/2, automatically you prove continuity of theta at PC in Z2 because you already have this. Okay, so the proof of this will use FKG inequality, but in a kind of convoluted way. So this is what I'm going to present now, which is called the square root trick. So this result is due to Vandenberg and Kesten, and the argument I'm going to present is due to Zhang. Is it the right pronunciation? Yeah, okay. So the trick we are going to use is called the square root trick, but really in the way we use it, it's more the quadratic root, no, not the quadratic root, the root to the power 4 trick. So what does it say? It says that if A is equal to A1 union AN, AIs are increasing. Yes, this is something I forgot to tell you. And PP of AI is equal to PP of A1 for all I. Then what you have is that PP of A is larger than PP of A1, sorry, is larger than 1 minus PP of A to the 1 over N. Okay, so what this result tells you is that if you have an event which can be written as a union of increasing events, and which have the same probability, then you know that if this event has a probability very close to 1, then all the events have probability close to 1. Okay, this is the way the trick will be used. Okay, and of course this is true. This is not true if you don't have the increasingness as an assumption. Okay, so basically, you know, the best you have in general is P of A1. If you don't have increasingness, what you have is that well, the union bound gives you this. Okay, this is much better because when this is very close to 1, then this remains close to 1. Okay. I mean, here, okay, n in general in the course so far, it was a parameter that was going to infinity, but here I'm going to use this for n equal 4. So. Okay. Yeah, maybe let's not call it n. Let's call it, I don't know, m. Okay, I'm going to use this only for a finite m. So how do you prove this? Well, it's just FKG. So problem is that FKG is for unions, for intersections. So what we are going to do is we say, well, if you look at the probability of AC, the complement of A, then it's equal to the probability of the intersection from I equal 1 to M of AI. Now, AI complement. Now, all these things are decreasing. Okay, so I can use FKG for decreasing events. So they are positively correlated. So this gives me that this is larger than the product from I equal 1 to M of PP AIC. So now if I write things in terms of the original probability, I get that 1 minus PP of A is larger than 1 minus PP of A1 to the power M. Here I'm using that all the events have the same probability. And this is basically the result, right? Yes. Yes, so you put this to the power 1 over M, and then you're pretty much done because okay, and okay, I don't think I'm going to use this anytime today, but I think it's a good thing to give as an exercise. If A and B are increasing, proves that A, B, and A union B are increasing. Okay, so this is the same as saying if you have two increasing functions, then the maximum and the minimum are increasing. The maximum between the two and the minimum. Okay, so here's the event A that we have in the lemma is increasing. Okay, so let's take just a small 5-minute break, and then we come back to prove the theorem. can continue. Okay, so, okay, let me tell you, why is this theorem true? So let's assume that it's not true, and then it would mean that you would have an infinite connected component in the primal graph, but because also the percolation parameter for the dual graph is 1/2, you would have infinite component in the dual graph as well. And just think about it. It looks very difficult to have one infinite component for the graph and the dual graph and for them to be unique. Because it means that this infinite component in the dual graph, it cannot split the other one into two. Okay? So the idea is to find a way to show that, well, actually, if you have theta p is larger than 0, okay, then necessarily the dual component will split the primal component into two infinite components, and then it will contradict uniqueness. Okay, so okay. So we have seen many times before. You know that when so assume that theta of 1/2 is positive. So we have seen many times that, okay, because of the uniqueness of the infinite component, no, not because you have almost surely an infinite component whenever theta is positive. This means that, well, this infinite component, it will have to intersect a finite box, which is large enough. Therefore, there must be, well, this finite box will be connected to infinity by a path that does not enter this finite box, okay? Only using edges that are outside the box. Okay, so the probability that gamma n is connected to infinity, this, it tends to 1. Okay, now this event, I will call it A. And I can write A as the union of 4 events. So A is equal to A north, union A south, union A west, union A east. Okay, so you just look at this path, linking the box to the complementer of the box to infinity, the one side of the box to infinity. So. And basically, you look at the first edge of your path. If it's going up, you say that A north is satisfied. If it's going down, you say that A south is satisfied. If it's going left, you say that A west is satisfied. So this means that this is really a partition of your events. Okay, I could say A north is just if you start from the north side. But by saying what I've said, I kind of clear what. Okay, what happened if you're on the corner. Okay, so if this would be that A north is satisfied, and this would be that A west is satisfied. Okay. So now all these things, so where let me write the definition of A north. So, the upper side of lambda n is connected to infinity with a path in omega, but restricted to n bar. Okay. So the edges that are not in the box. Okay. So now we are good because we are exactly in the. Okay, and this thing I can call it an, in fact. Okay, because we have a parameter n here. So here I'm just in the setup where I can apply the square root trick. All these events are increasing events. Okay, an event being increasing, it just means that it's more likely to happen if I open edges. And of course, here, if you give me more open edges, okay, if you give me a configuration for which this happens, and if you open more edges, then this will still happen. Okay, so from this, what we have is that the limit when n goes to infinity of pp a n is equal to 1. So if I take n larger than n0, okay, I can just say that this thing is larger than 7/8. Okay, here I've used something which we have not proved so far, but which can be left as an exercise. We know that the probability PP is translation invariant in the sense that if you take an event and its translation, they have the same probability. Well, it's also invariant by symmetries of the lattice. And it's for the same reason. Like it's obvious for cylinder events, okay? And then you can use the fact that cylinder events can be that cylinder events approximate any events. So this is the reason why all these things have equal probability, okay? Because A south is the image of A north by a reflection, and A west is the image of A north by a rotation by 90 degrees. Okay, and those are the symmetries of those are symmetries of the lattice. By the square root trick. Okay. We have used the invariance of PP by lattice symmetries. Okay. So now if this happened, what we can say is that, in fact, well, the probability that A north and A south happened is larger than 3/4. Okay, here I could use FKG to have 7/8 to the power 2. But this is just even the union bound. Okay, the probability of the complement is smaller than 2 times 1/8, which is 1/4. Okay. So what we have this is my box, and what we have is that with positive probability, we have one infinite path there, and another which is there. that are going to infinity. Okay, so now I will try to split them and to make them into two different components. So what's the idea? Well, I will look at this dual box here. Okay, so I will call, I don't know, lambda prime n, which is just n minus n plus 1/2 n minus 1/2 to the square. Okay, so it's the largest dual box which is completely included in lambda n. Okay, you remember that the dual lattice is just the original lattice, but it's shifted by 1/2, 1/2. Okay. So now, this is 1/2 here, 1/2 and 1/2. So now, if I look at the dual percolation process, so remember, it's defined by this. A dual edge is closed if a primal edge is open. Okay, and so you either have this or this. Okay, and now I can do the same thing. I can say, okay, the probability that lambda prime n is linked to infinity by a dual path that's going out of lambda prime n, it's going to 1 for the same reason. Okay. So Bn is equal, okay, to okay, but this is for omega star. Oh, okay, and then we can say, okay, Bn, well, it's equal to Bn north union Bn south union Bn west union Bn east. And using exactly the same argument, we can say that the probability that Bn east, Bn west are satisfied, it's larger than 3/4. Okay, for n larger than n1. Okay, this was for n larger than n0. Okay, and now we take n larger than the max of the two, and we're fine. Okay, so in particular, what we get from all of this is that the probability of A and north intersection B A and south intersection B and east intersection B and west, this is larger than 1/2. Okay, the important thing here is that it's positive. Okay, so here, I mean, somehow I couldn't use FKGs. These events are negatively correlated. I'm just using the union bound for the complement. Okay, the complement of this has probability smaller than 1/4. The complement of this has probability smaller than a quarter. So the union of the complement probability is smaller than 1/2. Okay. So now, so far, this looks quite good. So I know that I have infinite dual paths here going there. So if I want to show that the green paths cannot touch each other, well, one way will just be to connect these two paths together, okay, to make sure that they make a blockage there. And one way to do so is just to close all the dual edges inside the box, lambda n. Okay, and so far, I mean, when I look at these events, well, they actually only depend on, they only depend on the set of the edges which are either in lambda n, that are either outside of lambda n or on the boundary. Okay, the boundary edges are used when you look at these dual edges going out. You don't use them there. You don't use them there to establish the existence of the green paths. For these orange paths, you need to look at these boundary edges because it corresponds to dual edges going out of lambda prime n. Okay. So what's the definition of this? Yes. I think this was this. If I remember well, intersection lambda n minus 1. Okay, I defined the set of interior edges to be this. And now what I'm saying is basically the probability. Okay, let me call this event. How do you want to call it? Cn. So no, maybe just Cn like this. And now what I'm saying is that probability that Cn intersected with omega e is equal to 0 for all e in e n. Okay, this is positive. Okay, this is larger than 1/2 times to the power 1 plus the cardinality of En. Okay, I pay 1/2 for each of these, pay 1/2 for this. And these things are independent because the set of edges here are disjoint. This thing depends only on the edges of the complement. Okay, so in particular, this is positive. And now what I'm saying is that if this happens, then Z is larger than 2. Okay, so the next, maybe I will try to use 10 more minutes to kind of justify that maybe this should be the case. trying to justify why PC is a critical value. So we have just seen that at 1/2, for p equal 1/2, the probability of being connected to infinity is equal to 0. This means that the probability of being connected to the boundary of the box of size n decreases to 0. Okay? So now what we can show is that it does not decrease so fast. So we write this as a proposition. And this is on Z2. Okay, so let's first prove this, and then try to discuss why this indicates that 1/2 should be the critical point. And okay, so what's the starting point of this? Well, the idea is that at 1/2, okay, the percolation process and the dual percolation process, they look exactly the same. So for this reason, the probability of crossing a square from left to right, it should be, well, equal to the probability that the dual process crosses the square from top to bottom. Then you know that one is the dual process and the primal process, they are the same. One event then is kind of the image of the other one by a rotation of 90 degrees. So they should have the same probability. And because one is the complement of the other, they should have probability 1/2. Okay, so let's write this, and let's be a bit more careful because well, we have to be a bit more careful of what we mean by squares. And actually, what we mean by squares is actually a rectangle. So what will be my rectangle? It will be minus n times 0 to the 2n minus 1. Okay, so now what I'm saying is that, so this is what I will call, I don't know, Rn, and what I'm claiming is that the probability that there exists an open path linking the two on the left and right in Rn is equal to 1/2. Okay, so why is it so? Well, let me look exactly at my graph. So yes, so 0 is here. Yes, so it's like this and like this. Okay, so basically, okay, so let me. I should make a picture with n equals 3. This will be much better. So I I have 7 lines. 1, 2, 3, 4, 5, 6. No, I have 6 lines. Okay, and here I have 1, 2, 3, 4, 5, 6. Okay. Okay, so yeah, the length of my rectangle here, it's 2n, and the height, it's 2n minus 1. And if I look at paths from left to right, I can basically ignore if they make vertical moves here. Okay, I don't need these edges, because if the path use some edges like that, I can just start it after the last time it used an edge here. Okay, so if there exists a path linking left to right, basically there exists a path linking left to right that does not use these edges. This is the important part. Okay, let's not draw this because okay. Okay, so I'm only looking at this set of edges, and now this set of edges is exactly self-dual. This is the important bit, because if I just draw all the set of dual edges, well, then it will start. Okay, the dual edge here will be this one. The dual edge will be there, 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 and there. Okay, here I have no edge because I'm not considering this edge. Okay, so it's a mess, but you will believe me if I tell you that this orange picture is exactly the white picture rotated by 90 degrees. Okay, because if you count, you have exactly the same number of dangling hands. And, okay, so this is why you have 2n by 2n minus 1 and not 2n by 2n. Okay, just that when you take the dual, you obtain exactly the same thing. Okay, and now this is okay. So the proof of this. It's because the complement is the event of a crossing in the dual graph, and thus has the same probability. Okay, just because the dual graph can be superposed to the primal graph. Okay, when I'm in crossing, here I'm in top to bottom crossing. Okay. Okay, so now this path, it should start from somewhere. Okay, so this event, it's just the union of, well, there exists an x here such that there is a path starting from x going there. Okay, so from this, what I get is that there exists x in 0, 2n minus 1, okay, such that the probability that x is linked, okay, to the right side of Rn is larger than 1 over 4n. Okay? But the idea is that just that the sum of these probabilities is larger than 1/2. You have 2n terms, so one term has to be larger than 1 over 4n. Okay, so now when this happens, what you have is that actually x is connected to x plus lambda 2n. In omega. So we are basically, so this is that. Okay? Because this, by translation invariance, this is the same as this. Okay, so basically, why is this somehow? What I'm saying is that this decay, the fact that these things decay is like the power of n. Okay, we have only a lower bound, but let's assume that it's kind of a signature of criticality. This kind of indicates that 1/2 is the critical parameter, and the idea is that, well, for many models, what commonly happens in statistical mechanics is that basically it is believed that, well, your system has. Okay, so your PC, it separates the system into 2 phases, and it's believed that within one phase, the system always has the same behavior. Okay, so the idea here is that if you look at long distances, basically when P is smaller than PC, it really looks like P is equal to 0. So your lattice is very, very fragmented. You have only very small connected components. Okay, so it looks like if all the edges were closed. Okay, connections are really not going far. On the other hand, if P is larger than PC, your lattice is very well connected. And well, for instance, if you want to go from one point to the other on the percolation cluster, well, it should take the number of edges you should use. It should be more or less proportional to the Euclidean distance. So the unique infinite component that you have in your lattice, it should have more or less the same properties as ZD. And here you see different phenomena happen. Okay. And you see some kind of crazy pictures. And okay, so if you remember what we did during the first lecture, I think, is that, well, we kind of proved that this thing was smaller than, well, basically, 2d to the n times p. Just by saying, well, if this happens, then you have an open path of length n, and so the probability of having an open path of length n, it's smaller than the number of paths times the probability that a path is open. So in particular, when p is small, this decreases exponentially. And because basically everything should behave in the same manner in the subcritical phase, what you should believe and what we will prove is that when p is smaller than pc, then the probability that 0 is connected to lambda n is smaller than exponential minus cn. Okay, so if we can prove this, then this implies that 1/2 is smaller than PC. Okay, because no, it implies that PC, sorry, is smaller than 1/2, and therefore it completes our proof that PC is equal to 1/2. Okay, so this is what we will do next week, and yeah, so this gives you a picture. Okay, here, what you have is that here this decays to this converges to theta p, which is positive. Here, it decays like a power. And here it decays exponentially. Okay, so I think this sums up what I wanted to say today. Any questions? Okay, so we meet back on not this week, but the next.